Welcome to The Explainer. Today, we're taking a really close look at the sheer engineering magic behind autonomous vehicles. I mean, if you've ever watched a self-driving car navigate a completely chaotic city intersection, you already know it's a massive technical feat, right? Well, today, we're going to demystify exactly how these vehicles map and understand their environment in real time.
Let me throw a crazy paradox at you right out of the gate. How exactly does a self-driving car navigate if it suddenly loses GPS or doesn't have a pre-existing map? Think about it for a second. How can a vehicle build a map if it doesn't even know where it is? And, on the flip side, how can it possibly know where it is if it doesn't have a map to begin with? It's the ultimate chicken and egg scenario. Honestly, solving this is basically the holy grail of autonomous robotics.
Okay, let's dive into this. Here is our roadmap for today. First, we'll tackle that chicken and egg problem. Second, sensors and the SLAM loop. Third, the threat of moving things. Fourth, filtering the dynamic noise. And finally, we'll wrap up with the power of perfect data.
All right, jumping into section 1, the chicken and egg problem.
So, the answer to our little paradox is an acronym you absolutely need to know. It's SLAM. That stands for Simultaneous Localization and Mapping. This is literally the core superpower of any autonomous vehicle. It's the process where a vehicle estimates its own position while at the exact same time building a 3D map of its environment using real-time sensor data. It doesn't have to rely on some pre-built map because, well, it's continuously building and updating the map as it drives along.
Let's ground this in reality. Picture your morning commute. Let's say overnight, a construction crew set up from temporary highway roadworks and closed off your usual lane. Now, a standard GPS with a static map, it would just blindly tell you to stay in that closed lane. But in an autonomous vehicle using SLAM, it notices those completely new obstacles, instantly updates its internal map on the fly, and safely reroutes you into the open lane. It just seamlessly adapts to immediate, unmapped changes. A real game changer.
Moving right along to section 2, sensors and the SLAM loop.
Now, no single sensor is totally perfect, right? So autonomous vehicles rely on what's called sensor fusion. This is basically combining a bunch of different inputs for maximum reliability. LiDAR is the heavy hitter here. It blasts out lasers to create these highly precise 3D point clouds, essentially measuring the exact geometry of the world around it. Then you have cameras, which add rich visual context, like reading a stop sign or actually seeing the lane markings. Radar is in the mix too, and it's fantastic for measuring the velocity and range of other objects, which is super helpful even in terrible weather. And finally, IMUs, or inertial measurement units. These keep track of the vehicle's own internal velocity and physical motion so it stays grounded.
Once all those sensors pull in their data, the software completely takes over in a high-speed, continuous 3-step cycle. We call this the SLAM loop. Step 1 is perception. That's taking the raw, messy sensor data and extracting actual, meaningful features and obstacles. Step 2 is estimation. This is where it matches those new features against previously observed data to estimate exactly how far the vehicle just moved. But here's the catch. Over time, these tiny little estimation errors start to add up. It's a phenomenon known as localization drift. And that brings us to step 3, correction. When the vehicle recognizes a location it's seen before, a neat trick called loop closure, it mathematically snaps the map back into perfect alignment. It basically corrects all that accumulated drift so the vehicle stays on track and safe. All right, on to section 3, the threat of moving things. Early SLAM algorithms were built on this big, flawed assumption that the world is completely static. But we all know the real world isn't some empty, controlled test track. Our environments are chaotic. They are packed with dynamic objects, moving vehicles, pedestrians suddenly darting into the street, cyclists weaving around, temporary roadworks popping up. If a SLAM system treats, say, a moving delivery truck as if it's a permanent brick wall, the entire map gets corrupted. The vehicle's localization can literally fail catastrophically.
And this brilliantly illustrates a major headache known as ghost trail effects. Imagine a 3D LiDAR scanner hitting a walking pedestrian or a moving car over the course of several seconds. It's recording points for that object across multiple different locations as it moves. So when that's compiled into a 3D map, these moving objects leave behind these chaotic, smeared ghost trails. These trails are essentially dangerous noise. They obscure the actual static features of the scene, completely confusing the vehicle's perception and making map-based localization incredibly difficult.
Which leads us straight into section 4, filtering the dynamic noise. So, the million-dollar question. How do we mathematically scrub these moving objects from our maps? Well, two traditional approaches really dominate this space, and both come with some pretty strict engineering trade-offs. First up, the ray tracing-based approach. A famous example is Octomap. It's incredibly thorough. It divides 3D space into these tiny little cubes called voxel grids. If a laser ray passes straight through a grid that previously had an object in it, the algorithm says, aha, that object moved, and it deletes it. It's highly accurate, but man, it demands massive computational resources. On the other hand, we have the visibility-based approach. This one is way lighter and faster. It just checks if a new query point is visible behind a previously mapped point. Like, if you can suddenly see a building behind where a truck used to be, the truck must be dynamic, right? The downside, it struggles heavily with occlusion errors. It often misses large dynamic objects entirely.
Now, let's step into the modern era with the segmentation-based approach. Instead of just tracking geometry and bouncing lasers, this method brings deep learning and neural networks to the party. It tries to actually understand what the object is. The AI identifies specific semantic categories. It looks at a cluster of points and says, oh, that's a pedestrian, or that's a car. Once it identifies it, it just draws a bounding box around the object and completely deletes those dynamic points from the map. It's a brilliant AI-driven alternative, but it does have an Achilles heel. It relies totally on its training data. So it's highly susceptible to labeling errors, or it might completely fail to filter out some weirdly shaped unknown object that it just hasn't been trained to recognize yet.
And that brings us to our final section, Section 5, the power of perfect data, the true unsung hero in all of this.
As the team at Ncord so rightly points out, literally none of these incredible neural networks or advanced SLAM algorithms can function without high-quality human-labeled data guiding the AI. You could have the absolute best segmentation approach in the world, but if your deep learning model was fed poorly annotated sensor data, it's going to fail to recognize a pedestrian in the rain, or maybe it misclassifies a cyclist. To actually perfect SLAM, you need rigorously curated, highly accurate, and perfectly synchronized multi-sensor datasets. That is the only way to ensure these vehicles understand the physical world flawlessly. Which leaves us with this final, somewhat provocative thought to ponder. Can an algorithm ever truly map a world that literally never stops moving? I mean, SLAM has brought us incredibly far. It's turned chaotic, real-world environments into navigable, real-time 3D models. But as our cities grow more complex and unpredictable, the challenge for engineers and AI developers only deepens. It's this endless pursuit of precision in a dynamically shifting world. So what do you think? Thank you so much for joining me on this deep dive into SLAM today. Keep learning, keep questioning, and I will see you in the next explainer.